Welcome to this explainer. Today, we're diving straight into the next major leap in power electronics. We're breaking down BASiC Semiconductor's incredible silicon carbide, or SiC, discrete products. Specifically, we'll be looking at their Gen 3 MOSFETs, SiC SPDs, and hybrid devices. You know, if you've been following the massive shifts in electric vehicles or renewable energy lately, you're well aware that the hardware under the hood is changing rapidly. So today, we're actually decoding the specific components that are making that future possible.
Here is our roadmap for today. We're going to cover 1. The next power revolution. 2. BASiC's Gen 3 SiC breakthrough. 3. Advanced packaging, TOL and TALT. 4. Automotive-grade high reliability. 5. Head-to-head comparisons. And finally, 6. Real-world applications. Let's get right into it.
So, to start off, big picture, what's actually holding back the next generation of electric vehicles? Well, it really comes down to the limitations of traditional silicon. For decades, silicon has basically been the undisputed king of semiconductors. But in high-power applications, it has a really serious heat and inefficiency problem. And that thermal bottleneck, that is exactly what caps how fast an EV can charge or how far it can drive on a single battery cycle.
Section 1. The next power revolution.
The crucial point here is that silicon carbide is essentially the ultimate solution to those thermal and efficiency bottlenecks that are holding back modern power systems. Because SiC has a much wider band gap than traditional silicon, it can handle significantly higher voltages, operate at much higher temperatures, and switch states incredibly fast with very little energy lost as heat. And this applies across their entire lineup, from MOSFETs to SiC Schottky barrier diodes or SPDs. It's a total game changer.
Section 2. BASiC's Gen 3 SiC breakthrough. Now, check out this number, 30%. BASiC's Gen 3 technology achieves a massive 30% reduction in what engineers call the figure of merit, or FOM. You can think of FOM as the ultimate balancing act between electrical resistance and switching loss. So a 30% reduction translates directly into significantly less heat generated and much faster switching speeds compared to previous generations. It literally means you can push more power through a smaller space without melting your components.
What's really wild here is how these highly technical specs translate into huge wins on the assembly line. Take the active area resistance, which hits roughly 2.5 milliohms per square centimeter. That is absolutely world-class. But even better, BASiC has achieved such high product consistency with incredibly tiny deviations that manufacturers can just use these components in parallel without that tedious, expensive process of sorting them first. It's just a massive leap in manufacturing efficiency.
Section 3. Advanced packaging, TOL and TOLT. Now, having an incredible chip is only half the battle, right? How you package it determines how effectively you can manage all that intense heat. With traditional chips, they dissipate heat through the bottom, directly into the circuit board. But with innovative top-side cooling packages like QD-PAK and TOLT, engineers can actually pull the heat up and away, directly into a heat sink. This takes the invisible concept of thermal management and makes it a physical reality, allowing for much denser, much more powerful circuit designs.
And BASiC isn't just making one niche product here. They offer ultimate adaptability across the entire power spectrum. They are covering it all. We're talking everything from 650 volts all the way up to a staggering 1700 volts across all those advanced packages we just talked about, TLL, TLT, QD-PAK, and your standard TO247s. So whatever the engineering challenge happens to be, there's a specific package ready to handle the load.
Section 4. Automotive-grade high reliability. Let's transition from performance to trust. Because in high-stakes environments like EVs, failure simply isn't an option. Earning the rigorous AEC Q101 certification is no joke. It isn't just a rubber stamp. It proves that these hybrid SiC devices and full SiC modules are built to withstand the harshest automotive conditions imaginable. Think extreme temperature swings, constant vibration, and relentless electrical stress.
And how do they prove that kind of extreme reliability? Well, through brutal testing methods like the TDDB test. This specific protocol intentionally applies intense voltage to evaluate exactly how defects accumulate in the silicon dioxide layer over time. This is exactly how BASiC guarantees their components won't suddenly degrade and fail when subjected to the massive electrical currents required by modern EVs. They figure out precisely when and how the part will eventually fail, which allows them to confidently guarantee a safe, reliable lifespan.
Section 5. Head-to-head performance comparisons. Okay, let's dive into the hard data and see how this actually stacks up against the legacy industry giants. When you place BASic's 1200-volt components side by side with equivalents from Cree, ST, and Infineon, you immediately see BASic's competitive edge. For instance, looking at the total gate charge, or QG, BASiC hits 85 nanocoulombs. That beats out Cree's 99 and ST's 107. Simply put, less energy is required to switch the device on and off, and that translates directly to higher overall system efficiency.
The really crucial point here is the architectural choice. The industry constantly debates planar, which is a flat surface design, versus trench, which digs down deep into the silicon. Now, while trench might look great on paper with a slightly lower initial figure of merit, it has a fatal flaw. As it heats up, its resistance skyrockets, almost doubling. BASic's Gen 3 planar design absolutely does not sacrifice that high temperature stability. It maintains its rated current efficiently, even when the heat is fiercely on. And this advantage continues right into the 650-volt range. If we look at reverse recovery metrics, which is basically the energy wasted when the device turns off, BASiC achieves an ultra-low 0.16 microcoulomb charge. Compare that to Cree at 0.17 or ST lagging behind at 0.25. This data means smoother, safer operation with significantly less electrical noise and much smaller voltage spikes. BASiC has truly mastered the reverse recovery event.
Section 6. Powering real-world applications.
So we've seen the microscopic tech and the hard data, but where is this actually changing the world? These aren't just lab experiments, they're the backbone of modern infrastructure. From capturing and converting solar energy in photovoltaic inverters to handling the massive electrical loads of fast charging your EV, these SiC discretes are the invisible hardware accelerating the entire renewable energy revolution. They're making high-end welding machines more precise and power conversion systems drastically more efficient. And it all begins right here, at the microscopic level. A single SiC wafer is quite literally the foundation of the future. It perfectly combines relentless, microscopic innovation with rugged, automotive-grade reliability. Every single chip cut from this wafer represents a step toward a cooler, faster, and far more efficient electronic ecosystem.
As we wrap up this explainer, I really want you to consider this question. We rarely stop to think about the tiny components regulating power in our cars and our solar grids. But as BASiC Semiconductor continues to push the boundaries of SiC technology, ask yourself, when these components eventually cut charging times in half and push EV ranges well past the 1,000-mile mark, how will that reshape your daily life? Thanks for joining me on this explainer, and keep your eyes on the microscopic shifts driving our macro world.